Hey, happy Wednesday. So our lecture today, it's going to build off of yesterday's. It should be another short one. So just a reminder what we did yesterday. We were talking about this idea called percent composition. And if you were given a formula, you were able to tell me what percentage of that formula is composed of a certain element. So maybe what percentage is carbon, what percentage is nitrogen, things like that. Now that's going from a formula to a percentage. We're going to kind of do the reverse today. We're going to see that sometimes we'll be given the percentages. We'll know what the percent composition is. This is something that happens a lot, like certain machines can tell you what the percent composition is of a compound. And then our job will be to come up with the formula from those percentages. This is another very common thing in analytical chemistry, that you can figure out what the percentage is, and then you need to, as the human, do some math to figure out what the formula might be for that compound. So I've been using the word formula, but there's actually a few different types of formulas that we're going to be talking about. We got the empirical formula and the molecular formula. So let me move my face out of the way here for a second. What we're looking at here, like I said, two different kinds of formulas. The empirical formula is less specific. The empirical formula will tell us the proportions of the elements present in a given compound. It won't tell us the exact number of each atom of each element. It'll only tell us the ratio, the proportion. What I mean by that is maybe we have twice as much hydrogen as we do carbon. Maybe we've got 2.5 times as much nitrogen as we do carbon. It'll be able to tell us the ratio and the proportions, but not the reality. For the reality, we need the molecular formula. The molecular formula will actually tell us how many atoms of each element are in that compound precisely. So the molecular formula is really the stronger formula in my opinion, because it reflects reality and what those compounds are truly composed of. But the empirical formula is also useful because it's telling us the proportions of the elements in these compounds, which we can then use later for certain types of math, which we'll see. So two different types of formulas, empirical formula and molecular formula. We're going to do a few different types of problems going backwards from the percent composition to the formula. And I'm going to show you if we can figure out whether it's the empirical formula or whether it's the molecular formula. I'm going to show you what these problems look like on the next slide, but I think it'll be easier today if we can solve them on the wall here, rather than me trying to explain it through the slides. But let's take a little sneak peek here. So this first problem, it gives me grams. I know that I have 0.35 grams of this compound. So this is the total compound, 0.35 grams. 0.04 grams of that is composed of hydrogen. And then the rest of it is composed of oxygen. What is the empirical formula of the compound? So I'm starting with grams this time. I'm going to convert those grams into moles. I can do this with algebra or dimensional analysis. Remember, we use that molar mass formula. Molar mass is equal to grams over moles. So the first thing I need to do is convert these grams into moles. I would take this 0.04 grams and I would divide that by the molar mass of hydrogen, which is about 1. And then I would take this 0.31 grams and divide it by the molar mass of oxygen. That's going to give me two answers, two different numbers of moles. Whichever number of moles is the smallest, I'm going to use that number to divide both answers. And that should make me end up with whole numbers. In this case, it'll be H2O. And like I said, this will make a lot more sense when we do it on the wall back there. There is one more scenario that we might see. This time I'm not starting with grams, I'm starting with actual percentages. So I know that the compound is 27.4% sodium, 1.2% hydrogen, 14.3% carbon, 57.1% oxygen. And then I know the molecular mass. This is different from the first problem. In the first problem, I just knew the mass of the sample, which is not like a molar mass or a molecular mass. That's just the mass of one random sample. But this molecular mass, that's telling me exactly the mass of one molecule. So that's going to be, in my opinion, a little bit more useful. When you're starting with percentages, what you're going to do is multiply each percentage by the molecular mass. Remember that when we do that, we need to convert the percentages into decimals. So this would be 0.274, 0.012, 0.143, and so forth. I would multiply these by the molecular mass. And then I would take each of those answers and divide by the atomic mass of that element. And it should, again, give me whole numbers. In this case, it was 1 sodium, 1 hydrogen, 1 carbon, and 3 oxygens. Again, it's going to make a lot more sense to be easier to follow once we do it on the wall back there. But 2 different ways to approach it. If we're starting with grams, we're going to end up with the empirical formula, and we'll go through moles to get there. If we're starting with percentages, we will end up with the molecular formula, and we need to do that by multiplying by the molecular mass. So let's try it on the wall back there. We'll do probably 4 examples real quick, and then we'll wrap it up. But I'll do 2 examples of each, and I think it'll be easier to understand when I'm doing it back here. All right, here we go. All right, so we're going to try to get 4 examples in here. We're going to try to do 2 slow and then 2 fast, looking at empirical and molecular formulas. Let's look at this example first. I've been given the grams, the masses, for these 3 different elements. 50 grams of carbon, 5.6 grams of hydrogen, 44.4 grams of oxygen. Maybe I got this data from a mass spectrometer, a piece of equipment that you can run a sample through, and it would give you data like this. So I know the masses. I've also put the molar mass algebra formula up here. I know that most of you will be more comfortable with the algebra formula than the dimensional analysis. So I'm going to show this approach. When you're starting with grams, when we're starting with these grams here, it's going to be important that we use our molar mass formula and convert those grams into moles. The mole is going to be the more useful measurement here because moles are counting things. The mole is like an actual number, like a dozen. That means that if I have 1 mole of carbon, I'll have exactly the same amount of atoms as 1 mole of hydrogen. But 1 gram of carbon is not the same as 1 gram of hydrogen. That's because they have different molar masses. So I can't keep it in grams. I need to change them to moles. I'll show at least one of those here. For example, the molar mass of carbon, I know. I would look this up from the periodic table. It's about 12.01. We'll call that grams per mole. This is the molar mass of carbon, and I got that from the periodic table. I'll set up my algebra equation here. I know that I have 50 grams of carbon, so I want to know how many moles is that. Remember, we use N for moles. That's just the convention though. You can use an X if that's what's comfortable for you. You can use the word mole however you want to do it. It's just algebra here. So I've got it set up. I'm ready to solve for my variable N here. And I'm going to figure out that N is equal to, let me check my notes here, 4.1631. 4.1631, and this is moles. So I figured out that I have this many moles of carbon. I would do the same thing for my hydrogen and my oxygen. I'm going to go ahead and show those two. Here's carbon, hydrogen, and oxygen. I would use the same setup here. I would just need to switch some things out from the periodic table. For hydrogen, I would use, actually let's go ahead and show that. Got the whiteboard here, let's use it. So for hydrogen, I need to use hydrogen's molar mass. I'm still getting it from the periodic table. It's about 1.01. And I know that I have 5.6 grams of hydrogen. 5.6. I'll do my algebra just the same way that I did it that first time. And I'm going to find out that this will be about 5.5445 moles of hydrogen. And then finally I'll do the same thing for my oxygen here. So I have the molar mass of oxygen, which is just about 16 grams per mole. My sample contained 44.4 grams of oxygen. And if I do my algebra, solve for my variable, I'm going to get just about 2.775 grams, moles, my bad, is moles of oxygen. Alright, so there's my first step is done. I've taken all of these grams and I've converted them into moles. The next step, look for the smallest amount of moles and divide all of them by that smallest value. So my smallest value here is this one, 2.775 moles of oxygen. Let's clear some space here. So what I would do, I would take all of these and divide them by 2.2775. For one of them, that's going to be easy. 2.775 divided by itself is 1. So that tells me I'm going to have 1 oxygen. 1 O. I know it looks like 10. I'll do the same thing for the rest of these. 5.5445 divided by 2.775. This is going to work out to almost exactly 2. It might be 2.000 something, but it's going to be very, very close to 2. And it'll be clear that it's meant to be 2. So I'm going to leave it right there at 2 hydrogens. I'll do the same thing, the same format here for my carbon. So 4.1631 divided by 2.775. This is going to get me about 1.5. It's very, very, very close to 1.5. It'll be obvious that it's supposed to be 1.5. Now, this is carbon, I should say, carbon. I'm very close to my answer here. I can almost see it. What I'm looking for is an empirical formula. What is the ratio that these elements are coming in. I can kind of see the ratio now. I'll have 1 oxygen, 2 hydrogens, and 1.5 carbons. The problem is that I can't have half of an atom of carbon. You can't have half of an atom. I'm going to need those to be whole numbers. Easy fix here. If I double all of these, that's going to make all of them whole numbers. So, I'm doubling all of them. This becomes 2 oxygens, 4 hydrogens, and 3 carbons. And that is my final answer. So this formula, starting from this mass data, I did some algebra, and I was able to get my empirical formula. Remember I said I doubled all of these. So this is 2 oxygens, this is 4 hydrogens, and then this is 3 carbons over here. So C3, H4, O2. This is my empirical formula. It's only telling me the ratios of these elements. This might not be the reality for this compound. What I mean by that is that it might be the same ratio, but in different amounts. Maybe the actual molecular formula is C6H8O4. It keeps the same ratio, but it's a different composition. I've got twice as much of all these things. The empirical formula will always be the simplest ratio of whole numbers. So I couldn't use the 1.5, but I'm going to stop it once I get to these numbers here, the simplest whole numbers that I can use for my subscripts. So this is an empirical formula that I just solved for. We did one slow. Let's do one more of those fast, and then we'll move on. Alright, so we did a slow one. Let's see if we can't pick up the pace. I said this was going to be a short video, and it's turning out longer than I thought. So this time, I'm still starting with masses. They're masses because they're in grams. I've got carbon, hydrogen, and fluorine. The first step is to use the molar mass formula to convert these masses into moles. I'm not going to show that algebra this time, but I'm plugging and chugging here using molar masses from the periodic tables and the grams that I'm given. What I would find out is that I'm going to have 3.03 moles of carbon, 6.04 moles of hydrogen, and then 3.03 moles of fluorine. So you can see what I mean, that it might not give you whole numbers, but we can tell what the whole numbers are meant to be. These are really close to whole numbers here. It's off a little bit because of all the small decimals that we have to work with. So what I'm really looking at here is approximately 3, approximately 6, approximately 3. I can go ahead and write my formula right from this. C3, H6, F3. Now, this is not my empirical formula though. I told you the empirical formula needs to be the simplest whole numbers that can make that ratio. I can simplify this. So I'm going to divide it all by 3. We'll say CH2F. This is my empirical formula right there. So there's a fast one. Now let's see if we can come up with these molecular formulas when we're working from percentages instead of mass numbers. So we switched it up. This time we're trying to find the molecular formula. And I'm starting with some different data. It's giving me the percentages, the percent composition for each one of these elements, hydrogen, sulfur, and oxygen. And it gives me a new piece of information. I know what the molecular mass is. One molecule of this compound will be 98 atomic mass units. My job is to come up with the molecular formula. I think that these problems are actually easier than the empirical ones. What you're going to do, take these percentages and multiply them by the molecular mass. So we're going to end up doing this 3 times. Remember that when you multiply by a percentage, we need to change it into a decimal. So I'm setting this up 3 times here. 2% as a decimal, 0.02. And that's times 98. This one as a decimal, 0.327. That's times 98 as well. Change this last one into a decimal. Multiply that by 98 as well. The 98 is the mass of the entire compound. Now I'm trying to figure out what's the mass of each element. So I take the total mass and multiply it by the percentages. My answers that I'm going to get here, I wrote those down. For our hydrogen, we're going to get about 1.96 grams of hydrogen. For our sulfur, we'll get about 32.05 grams of sulfur. And for our oxygen, it is just about 64 grams of oxygen. So I started with the percent compositions, and I've changed these into actual mass numbers for each element. So I know how much, in terms of grams, I have of each one of these elements. And I'm sorry, these should actually be in atomic mass units, since I was starting with a molecular mass and not a molar mass. That's my bad. So these are actually in AMUs here. My last step is going to be to divide these numbers by their atomic masses, which I'm getting from the periodic table. So 1.96 AMUs divided by the atomic mass of hydrogen, which is just about 1.01. I'm going to get roughly 2. Just about 2 atoms of hydrogen. I'll do the same thing for sulfur. Divide by that atomic mass, which I got from the periodic table. This one works out almost perfectly. 32 divided by 32, I'm going to have 1 sulfur. And then I'll do this same thing down here for oxygen. And this one works out really well too. I'm going to have 4 oxygen atoms. So my molecular formula for this compound will have 2 hydrogens, 1 sulfur, and 4 oxygens. If I write that out, H2SO4. So I'm starting with data. My data this time is the percent composition. I'm given the molecular mass. With that percent composition data, I figure out the mass data. What is the mass of each element in this compound? And then I divide by the atomic masses to find the number of atoms in each molecule. 2 hydrogens, 1 sulfur, 4 oxygens. That's my slow one. Let's see if we can't do one more of these molecular formulas at a little bit faster pace. Here we go. So we're going for one more, and we're picking up the pace a little bit. We're still looking for a molecular formula, and I'm starting with percent composition data. So I'm going to do the same thing I did last time. I'm going to take each of these percentages, multiply it by the molecular mass. My molecular mass is very big this time, 695 atomic mass units. I'm going to end up with a big compound, but let's check it out. So, taking these percentages, changing them into decimals. There's 1 decimal, all I've done so far is I took these percentages, changed them into decimals. All of these decimals are getting multiplied by the molecular mass, 695. This is going to tell me the mass of each element in this compound. I've worked these out. So we'll get about 185.6 atomic mass units of phosphorus, 84.1 AMU nitrogen, 425 AMU chlorine. So these are big amounts here. Each one of these mass amounts, I'm going to divide by the average atomic mass of that element. I'm looking these up from the periodic table. Phosphorus is just about 31 atomic mass units. Nitrogen's just about 14. Chlorine's about 35.5. It's not going to give me exactly whole numbers, but it's going to be so close that it should be obvious what the whole number is meant to be. So I'm going to have just about 6 atoms of phosphorus, about 6 atoms of nitrogen, and about 12 atoms of chlorine. If I take these numbers and put them into a formula, I'm going to get P6, N6, Cl12. So like I said, a very big compound, a big molecule here. Now, this time, I was solving for the molecular formula. So I am not going to simplify. If this were an empirical formula, I would want you to simplify it to PnCl2, divide them all by 6. We don't need to do that with a molecular formula. I know exactly what the mass of this molecule should be. If I simplified it, the mass would not be big enough. So that's the difference between the empirical formula and the molecular formula. With the molecular formula, I know what the molecular mass is, so I can use that. With the empirical formula, I'm really just looking for the ratio between those elements. And it might be, half as much, or it might be twice as much, but the ratio will stay the same. So that's the big difference between empirical and molecular. Your homework is, again, very short tonight, 2 problems. One where you're looking for empirical, one where you're looking for molecular. We'll have a quiz tomorrow. That's going to be over percent composition, empirical formula, and molecular formula. All right, come to office hours if you have questions. Email me if you have questions. Use the chemistry chat room. See you tomorrow.